Imagine a spacecraft that needs no onboard propellant, no tanks of gas to deplete, no toxic hydrazine to handle, yet still accelerates through the void. Could we exploit pure electromagnetic fields and plasmas to push a ship forward rather than hurling out reaction mass? How do conventional plasma thrusters work? Most electric propulsion systems, Hall thrusters, ion engines, magnetoplasma dynamic MPD thrusters, create and accelerate a plasma, then eject it at high speed. The expelled ions carry momentum away, pushing the craft forward. Question: can we just leave out the exhaust and still get thrust? Answer: not without something else to push against. Conservation of momentum demands a reaction partner, usually the propellant itself. Hey, what if the reaction mass is the ambient medium? In low Earth orbit or within planetary magnetospheres, there's tenuous plasma floating around. A Magnetoplasma Sail, MPS, uses electromagnetic fields to scoop up these charged particles, accelerate them backward, and gain thrust, effectively using the ambient space environment as reaction mass. But once you leave that plasma reservoir, say in deep interplanetary space, you lose your free propellant, and the fields alone can't push you onward. Could pure fields carry momentum? Electromagnetic radiation does have momentum. That's the principle behind photon rockets and solar sails. A perfectly reflecting sail can transfer twice the photon momentum per bounce. Yet even sunlight's scant photon flux yields micronewtons per square meter, a gentle push that takes years to build useful speed. If you instead trap and bounce microwaves inside a closed cavity, the controversial EM drive, you're hoping the internal fields somehow transfer net momentum to the ship. Countless tests have produced ambiguous results. Most fall within experimental error because without ejecting anything, momentum conservation seems to forbid a net push. What about exotic field interactions? Theorists have mused whether coupling to the quantum vacuum or manipulating spacetime itself could produce thrust without expelling mass. Mach effect thrusters claim to tap transient mass fluctuations under high-frequency fields, but independent replications remain elusive. So far, no field-only scheme has demonstrated sustained, reproducible thrust that can't be traced back to some hidden propellant leak or experimental artifact. Where does this leave us? True reactionless propulsion remains a dream because every successful thrust mechanism, whether ejecting ions, reflecting photons, or harvesting ambient plasma, ultimately exchanges momentum with something. Fields are powerful tools for shaping and accelerating plasmas, but they can't substitute for the fundamental bookkeeping of momentum. For now, the most promising path combines high-efficiency plasma thrusters with occasional photon or solar sail boosts, rather than a pure field-only drive. In the end, whether we're pushing propellant or bouncing light, a spacecraft must always push back against some partner, be it particles, photons, or the sparse sea of space itself, to move forward. Classical rocketry and propulsion are governed by Newton's third law. Every action must have an equal and opposite reaction. This means a rocket must expel mass, propellant, to generate forward thrust. The reaction mass carries momentum away, pushing the spacecraft forward. All traditional propulsion systems, from chemical rockets to ion thrusters, rely on this principle. The idea of propelling a spacecraft without ejecting mass would seemingly violate this fundamental law, unless new physics or overlooked mechanisms are involved. NASA's SLS rocket burns liquid hydrogen and oxygen to produce thousands of kilograms of hot exhaust expelled as reaction mass. It's like trying to jump forward while standing on ice. You need something to push against. Plasma thrusters like Hall effect and Vasium engines still expel ions as propellant, but use electromagnetic fields to accelerate the plasma. These systems are more efficient than chemical propulsion and operate in deep space, but still rely on reaction mass. The promise of reactionless or propellant-free plasma propulsion would require manipulating the fields themselves as momentum carriers. Some concepts explore using plasma oscillations or magnetic bubbles to couple with the vacuum or external fields. The boundary between field momentum and mass momentum becomes critical in these designs. The Vasium engine uses radio frequency waves to ionize and accelerate argon or xenon plasma, achieving high specific impulse. It's like blowing air through an invisible trumpet. The instrument adds control, but sound still needs a medium. Maxwell's equations show that electromagnetic fields can carry energy and momentum in the form of pointing vectors. In theory, a system that changes its field configuration might radiate momentum into space. However, if all changes are internal and radiation is confined, there should be no net external thrust. For true propulsion, the system must interact with the outside environment, such as space-time, the quantum vacuum, or a distant field. This leads to interest in non-local coupling mechanisms and exotic field geometries. Light sails work by reflecting photons from the sun. Photons carry momentum even though they are massless. It's like sailing on a wind you cannot feel, but only if you catch it at just the right angle. The M-Drive is a controversial device that claims to generate thrust by bouncing microwaves inside a conical cavity. If true, this would defy conservation of momentum, as it uses no propellant and produces no radiation leakage. Critics argue that any observed thrust results from experimental error, thermal gradients, or magnetic interference. NASA's EagleWorks team reported small thrust levels, but results were inconsistent and unreplicated. No peer-reviewed experiment has definitively validated net momentum transfer without mass expulsion. A 2016 paper reported 1.2 mn of thrust in vacuum tests, but later replication efforts showed null results or thermal artifacts. It's like claiming you can row a boat by splashing water inside it. Plausible only if water escapes the system. Some theories speculate that the quantum vacuum itself could act as a reaction partner, offering virtual particles or fluctuating fields to push against. This idea, while speculative, arises in studies of the Casimir effect, where boundaries modify vacuum energy. If a device could interact asymmetrically with vacuum fluctuations, it might extract usable momentum. However, quantum field theory maintains strict conservation laws, and no experiment has shown directional thrust from vacuum interactions. Such systems remain highly controversial and unproven. Theoretical proposals like the Woodward Effect and Q-thrusters suggest vacuum inertia changes, but lack rigorous confirmation. It's like trying to paddle through fog without knowing if the fog can push back. Some proposed systems use high-frequency plasma oscillations or rotating magnetic fields to create differential forces inside a confined cavity. These oscillations could, in theory, shift momentum between modes or create local pressure differentials. However, unless part of the momentum escapes the system, as radiation or mass, the center of mass remains stationary. Systems that radiate energy, as in directed electromagnetic pulses, could generate thrust, but they are not truly reactionless. The distinction between internal oscillation and external emission is critical. Pulse plasma thrusters produce tiny thrusts by ablating and ionizing internal propellant via arcs, but still expel particles. It's like shaking a bottle of soda. Unless you let the gas out, the bottle won't move. Relativity imposes strict symmetry and conservation laws on isolated systems. Any propulsion without mass must either emit radiation, distort spacetime, or exploit external fields. Asymmetric field geometries can appear to produce internal forces, but do not yield net external thrust unless part of the field escapes. Some speculative devices attempt to shape standing waves or field stress tensors to mimic propulsion. Without net energy momentum flow leaving the system, propulsion remains impossible. In classical electrodynamics, asymmetric field geometries produce internal stresses, but no net force unless the system radiates. It's like twisting a balloon inside a sealed box. The box doesn't move, even if the balloon reshapes. Many laboratory anomalies in reactionless propulsion can arise from hidden forces: thermal expansion, magnetic coupling with Earth, RF leakage, or instrumentation errors. These false positives can mimic real thrust, especially at micronewton levels. High sensitivity force measurements must be shielded from thermal, acoustic, and electromagnetic contamination. Einstein's equivalence principle ensures that any unbalanced force must be measurable through external interaction. Disentangling legitimate thrusts from artifacts remains a major challenge. Some EM drive thrust reports were later traced to power cable interactions or thermal radiation recoil. It's like feeling a push on your hand, not from magic, but from the fan you forgot was running nearby. To date, no plasma or electromagnetic propulsion system has demonstrated sustained thrust without mass ejection or radiation emission. While fields can manipulate and accelerate plasma efficiently, they cannot create net motion unless part of the system exchanges momentum with the environment. Claims of reactionless drives remain unproven, though some inspire valuable exploration in plasma physics, vacuum energy, and quantum field dynamics. The dream of massless propulsion remains alluring, but it must obey the laws of conservation and causality. Future breakthroughs may involve coupling with space-time or engineered quantum vacua, but they are not yet reality. All existing spacecraft, from ion engines to solar sails, obey Newton's laws by pushing against mass or photons. It's like dreaming of flying by waving your arms. Beautiful in theory, but gravity still asks for